All right, so let's begin, given that we are a little bit behind already. So, today is yet another application of the same method that we've been seeing for a bunch of lectures now. And so today the example that we will discuss in more detail is this this whole line of work on list decodable learning. We'll see one example as usual, and I'll get to tell you about some new aspects that might be interesting in designing algorithms with the sum of squares method. And so one new aspect that we'll study today is this idea of maximum entropy pseudo distributions and how they play a role in algorithm design. Good. And as usual, I'll request you all, whoever can, to turn on their videos. It's not mandatory as usual, but if you can, it's always good. So good. As I said, this is yet another application of the same method. By the way, I should remind you, the link to the scribble for today is on Didero. We don't have Peter here today, so I think it has not been posted on chat. So if someone is unable to find the video, the scribble link, let me know, and I'll post it in the chat. But it is updated in that single post that Peter uses on Didero. Good. So yeah, so we're going to see yet another application of the same method, that uses certifiability proofs for solution and uses it to design algorithms, efficient algorithms. And today's example is basically a research direction with lots of recent recent activity, lots of different papers being written on this topic. We'll see one example only. Currently active, and it's kind of a very nascent area. Most of the works that have happened in this area are about 2 to 3 years old, so it's extremely current. And the main motivation of this area is to design algorithms for problems that might have some relevance in machine learning, etc. And you want to design algorithms in order that they be able to tolerate a humongous fraction of outliers, a humongous fraction of corrupted samples, and the corruptions are fully malicious in this regime. So malicious corruptions. And it's part of this large portion, maybe the last 7-8 years or whatever, on this area of robust machine learning, where you want to design algorithms that are somehow not fooled either by malicious or benign corruptions in the data that you use to learn from. As usual, we will not focus on the motivation, because the goal of this seminar is to focus on the methods for algorithm design. So we will not care so much about where the problem comes from, as long as we are all convinced that it is somewhat interesting. And so, I'm just giving this broad 1-minute thing for you to find some broad context, but, I will not go into detail about why we care and what's this whole area about, etc. Good. So our main interest is actually, in some of the new ideas beyond what we've already seen in terms of, using the sum of squares method to design algorithms. And so in that, some of the points that you might notice today, and I want to point it out early on, is, okay, so, new conceptual ideas in, in algorithm design using the method we studied today. So, one idea that you will see that so far our rounding algorithms, if you remember, okay, they've been rather simple, but still, somewhat, I guess eventually it was reasonable to explain why we came up with it, but they were like, oh, okay, retrospectively easy to verify. Perhaps you might wonder, how do we come up with it? So today, we will actually face this problem in a slightly bigger measure, in a certain sense. At least there would be no natural rounding algorithm, that will give us the solution we would want. And so you'll see how the same philosophy that we follow in designing designing like certifiability proofs, we will be able to push that philosophy even to like somehow spitting out and rounding algorithm for us. And this view, where we view all proofs as sum of squares proofs, and dually, all pseudo distributions as caricatures of actual distributions, would be helpful in even coming up with a rounding algorithm. So we'll study how to use the distribution view to come up with something that might look like a very odd rounding algorithm if you weren't coming from this point of view. Okay, so distribution view to come up with roundings. So we'll see, you'll see that example. You'll also see that even though in a certain sense, and we didn't discuss it in detail, but this kind of thinking has to come up in the right algorithms for tensor decomposition, which we saw. Today, it would be crucial that we don't just compute any pseudo distribution that satisfies a bunch of constraints. Indeed, it would be important to find what would be some analogs of maximum entropy pseudo distributions. And so you'll see why that is important and how we will use it. So so use of max entropy pseudo distributions. This is kind of ill-defined idea right now, right? Like, what does it mean to define entropy for pseudo distributions, and what does it mean to have max entropy pseudo distributions? How can we find them, etc.? We'll see it in some more detail, but you'll see in some sense, any pseudo, like so far, our algorithms have worked by finding any pseudo distribution that is consistent with a bunch of constraints and is of high enough degree. Today, that won't work. Today, we will have to rely on somehow, using a distribution that satisfies a bunch of constraints and minimizes certain notions of entropy. So we'll see that. And actually, some non-standardness might appear right away in even the notion of a certificate. And so, that also might be somewhat interesting to look at. Good. So those are things for you to keep in mind as we go on to the lecture. And okay, given that we don't have Peter today. Oh, thank you, Akash. I guess Akash is serving the role of Peter. Maybe I should stop with where I was going, given that we have Akash now. But I'll try to monitor the chat, regularly, so that I can answer questions on the chat too. Something that I wasn't doing very actively in the previous lectures. Good. All right. So we pontificated a lot. We have not even defined the problem. So let's do that. So what's the problem we're going to look at today? So, I'm going to call this problem list decoding of noisy linear equations. And here is what it means, okay? It's very simple, very direct, very clean question. So, okay, so let's maybe write it like this. Suppose I give you a bunch of x1 y1 so on up to x. Actually, you know what? Let me call it xn prime yn prime right now. I'll soon replace this n prime notation with something else because you'll see I'm going somewhere. But right now, let's say that I have these xi yi pairs. And what I know about these pairs is that each of these xi yi are as follows. Xi's are d-dimensional vectors. Okay, so d, as in the previous lecture, serves as a dimension, and y's are just real numbers. So as usual, remember when we design algorithms, we have to work in the rational model, but we're going to ignore that distinction. Good. And let's say that that there is some L star, which is some vector in the dimensions, and you have the guarantee that for all I, yi equals the inner product of L star with xi. Okay, in other words, the yi's are basically evaluations, of a linear function on the corresponding xi's. Okay, and suppose I gave you this bunch of equations. Okay, and I asked you to calculate L star. How can you do it, or can you do it? I have begun my round of silly questions. So this is the first one. Who wants to go ahead and tell me whether this is an easy problem, hard problem?
Linear regression. So,
Yeah, so Tim speaks like an ML person, but Tim, these are linear equations. You don't have to do any regression. You simply have to do Gaussian elimination.
oh yeah.
There is no noise. There is no regression business going on here. You're simply, trying to calculate a vector, that satisfies a bunch of linear equations. Okay. So Tim is right, though. What we want to do today is also to adjust to noise, etc. But I'm going to completely ignore that part. Okay. We're not going to focus on the noise part. In order to make sure that we are doing something not of interest to machine learning, we will ignore noise. Okay. So that's good. But let's, before going on, make the one important observation. Um, there is, like, in general, you're not guaranteed a unique solution. So if I ask you to find a solution, that's a different question than finding L star. Okay. So the question I am interested in is always, finding L star. I'm not really interested in finding any solution. And notice that that's not possible unless, for example, xi's define a linearly independent set of equations. Okay. So anyway, so the summary of this trivial question is that if xi's, so observation, if xi's are linearly independent, then can find L star by Gaussian elimination. Good. All right. So that's not the problem we're going to look at today. We're going to look at like a twisted version of this. So now what we're going to do is, this is not going to be our input. We'll we'll choose some alpha. Think of some alpha as a fixed constant. Well, let's say right now just less than 1, but eventually, alpha would be a tiny constant like 0.1. So let's say, alpha is some fixed constant like this. And now imagine that I set n prime to alpha n. So, I'm trying to construct a set of n equations, an alpha fraction of which are basically, drawn according to this model that we just discussed. They are basically, imagine that they are linearly independent. Imagine that, there is some unique solution L star to them. And if we were just given this set of equation, then we will be done, right? We will just do Gaussian elimination and we'll be able to calculate L star. Instead, you're going to be given a corrupted input. And this input looks like x1, y1, so on up to xn, yn. So I'm always going to call it S for sample, right? And the guarantee is that S contains, a original uncorrupted set of size so like there is some unknown alpha fraction within this sample, which is satisfied by some fixed L star. And I don't get to see those. I simply get to see a larger set, which is, let's say, you can imagine that it's being obtained by taking this alpha fraction of good equations. So, in fact, I'll use that notation and language throughout. We're going to call this set good set, G for good. Okay. And so S can be thought of as good set plus bad set. And the bad set is of size 1 minus alpha n. Okay. And now what's my goal? So now, let's set alpha to be something, tiny. Let's say, alpha is even less than half. Okay, you'll see in a second why I think half is a interesting number as a threshold. And so now, for this model, I can ask the following question. Find L star. Is this possible? So given this set of samples, G union B, G is of size alpha n, B is of size 1 minus alpha n. Think of alpha as like, 10%. So, 10% of the samples are good, 90% of the samples are, corrupted and perhaps maliciously corrupted. So, Tim generated it for you. with the hope that he would be able to stop you from finding L star. And your goal is to see if you can find L star. And the question is, can you do it? That's my silly question number two.
If more samples are corrupted than uncorrupted, then you could just have another L hiding there.
Exactly. So what Misha is saying is that this is provably impossible. And the reason is, well, somehow, the bad samples could simply contain another alpha n size set. And if 1 minus alpha is bigger than alpha, then this is always possible. And the bad samples could contain another alpha fraction of the alpha n size set, which is soluble by a completely different L star, completely different vector. And there is no way for you to tell the difference between, this good pretending subsample of the bad part from the actual good part. How can you tell? And if you can't tell, then how can you find L star uniquely? And so this is provably impossible. Hopefully that's absolutely clear. Again, feel free to stop me and ask questions, okay? So instead, we're going to relax our goal. So that's not going to be possible. Instead, our goal would be to find a list L, and this list would be of candidate, vectors. It's a list of size k, okay? And I want the guarantee that L star should be in L. Eventually, I've relaxed it to, L star being close to some vector in L. But let's, continue with this ideal goal for now. So I can't expect you to find L star uniquely because there is, because only 10% of the samples are good. But I still want to recover in some sense, as good a piece of information I can about L star. And, I'm saying, hey, you know what? If this is all you can do, if 10% of the samples are good, and all you can do is like somehow, make the bad part contain as many confounding sets as possible, then, maybe you will be able to take the bad part and split them into 9 different 10% samples, each, satisfied by a different vector. And so even in that case, I should be able to produce a list of 10 hypotheses, 10 candidates, such that one of them is a correct candidate, right? And so this 10 is basically 1 over alpha in general. In general, I can expect to find about 1 over alpha candidates, such that one of them is always a good, one of them is always the truth I was after. Okay, so that is going to be our goal.
So do we know how many sets S we can squeeze into one set of size n?
What does that mean?
So given a set of size n, how many sets of size alpha n could exist inside such that for each set there exists an L star?
Yeah, I will prove in like 15 minutes or 10 minutes that exponentially in the dimension number of things can exist.
Okay, so 1 by alpha is the lower bound, as you said. You can
1 over
just
alpha
split
is a lower
into
bound.
disjoint.
Yeah, but if all you want to do, okay, so Praneeth is asking an important question, and let's maybe focus on that, even though I am going to get to it in somewhat more detail in a second. So Praneeth is saying, hey, you know what? Look at B, okay? This vague, shady calculation that we just did, that if, we just like take B to be a union of 9 different 10% size sets, each of which is labeled correctly according to some, different linear function. If this is all that the adversary could do, then, it seems legitimate that it should be easy to calculate like a candidate list of size 10, right? But Praneeth is observing that, well, why there is no necessity a priori that B should be uniquely splittable into like, 10 different candidates with 10% equations, associated with them, right? And in particular, there could be many, many ways to take B and split them into, 10% size subsets, each of which is satisfied by some, different linear function. And if there are many, many ways, in particular, much larger than 1 over alpha, in particular, something that grows with the dimension, which is a big no-no for us, then, at least this particular vaguish calculation already looks a little bit problematic. And notice that in this problem, we never, ever have any control on the bad part. The bad part is completely malicious and, is chosen after looking at the good part. So the adversary can go and like look at your good part and do all that he wants. They can run exponential time computation if they like, or whatever, unbounded time computation if they like, and then decide their choice of B. So we have no control absolutely on B. So, we can't quite force B to be nice in any way. Okay, we can only force G to be nice. Like good part is what we can control. Bad part we have absolutely no control over. Okay, so we'll soon see that this problem is going to be insoluble. If all that we know about the good part is that it contains a linearly independent set of equations, we'll need to make more assumptions, and we'll actually do some brainstorming to get to the right assumption very soon. Praneek, does that answer your question somewhat? Did he reply on chat? Yeah, he did. Okay, good. So cool. Okay, so let's proceed. Okay, so I have told you what our goal is today, and I can tell you what we're going to prove today. So we're going to prove, we'll show a d to the o of alpha to the 4 eta to the 4 time algorithm, or actually maybe the right way to write it is n to the 1 over alpha square eta square time algorithm to calculate a list of size O of 1 over alpha such that there is an L hat in this list satisfying L hat minus L star is small, let's say eta times the norm of L star. Whenever S satisfies not S, G in S satisfies some niceness condition. What that condition should be, we'll soon decide. But basically, when G, the good part, satisfies some additional assumptions, then no matter what the bad part is, we will be able to compute a list of size about O of 1 over alpha. The running time we'll spend is this. Now, it depends whether you want to feel happy about this or sad about this. It has 1 over alpha and 1 over the accuracy appearing in the exponent. So it's pretty bad in a certain sense. But at least if you're going for a constant accuracy and alpha is a fixed constant, then this is a polynomial time algorithm. In any case, it will be a non-trivial algorithm, as in as you will see that there is no other algorithm that we know for this problem that does better. It turns out that by some other techniques which appeared later, we can actually make the dependence on eta a little bit better. So we can replace this 1 over eta square by log 1 over eta, but we will not do that today. Okay, actually, we will not see that in this class because it's rather messy. But yeah, so today this is our goal. Okay, this is what we're gonna see. Good. Okay. So, all right. And I'm gonna now write a line that I've written many times. Focus on certificates. Now you're no longer surprised when we try to solve the problem. When we try to, in particular, solve the search problem, we instead, don't try to solve the search problem directly. We instead focus on the problem of verifying or certifying purported solutions, right? And then we try to develop a test for checking solutions. We try to establish its completeness and soundness. We try to phrase the test as, a bunch of polynomial inequality checks. We try to phrase the conclusion of soundness as a certain new polynomial inequality. And then we try to compute a pseudo distribution and try to round, right? Like this is something that we have done over and over again. That's also at a high level that we're going to do today. Okay, so let's focus on the certificates. Okay, good. So what's the solution here? Well, the solution is a linear function. So the first potential thing that you can ask a prover who is trying to convince you that a certain L is a solution, right? So what can they give you? Well, they can give you, so the first cut is the prover gives you L, some vector, and claims it's a solution. I claim it's a solution. Can the prover ever be right about this? Well, no, because information theoretically, we know there is no way to uniquely identify L star when alpha is less than half. So there is no hope for the prover to be right if they, specify exactly one L to us, right? Even if they are right, even if they are like, they saw the original sample being made, there is no hope for us to be able to verify their claim. Okay, so this is not going to work. The prover is going to have to give us something more. So the second cut is the prover gives us, let's say, a list of k different linear functions, k different vectors, right? And the prover comes and claims, hey, you know what? I think your function is in this list. Okay, and we are asked to verify their assertion. Can we verify? How can we verify? What should we do? What check should I make? Silly question number 3. Somebody hands over a list of potential solutions to me. They're saying, you know what? One of these LIs is your favorite L star. What can I check about LIs?
Check how many constraints they satisfy.
Right, exactly. So I can just try to check if well, in some sense, what do I know about my true good great L star? I know that L star satisfies some alpha fraction of the solution. Well, I know that it satisfies the good part of the solution, but I don't really know any other property of the good part, so I don't know what to check. So what I can try to check right now is simply see if each of the LIs satisfies some alpha fraction of the solutions, right? Actually, we can make our task easier that way. We don't even have to try to solve equations. The prover is all powerful. They can generate, they can, for each Li, they can actually also hand over to us the equations that Li is supposed to satisfy. So, we'll ask for the prover not only to give us L1 through Lk, we will also ask them to give us S1, Sk. Each Si is of size, let's say alpha n. Okay, the size of the good set, and we'll assume that we know alpha. And we can check Li inner product xj equals yj for all xj yj in Si. Make sense? Seems like a reasonable thing to do, right? Good. So we definitely checked that there is some alpha size subset of equations that each Li satisfies. But that's not what I want. Remember, my goal is not to compute a bunch of solutions to the system of equations. My goal is to compute L star. My goal is to find out what this L star was, and at least a small list that contains L star. So the question is, and this is basically the question that Praneeth was asking earlier, how large does K need to be how large does K need to be so that any list that passes the checks that I have here, contains L star? Okay. Silly question number 4. What do you think is the answer to this question? Oh, I'm going to call each of the SIs soluble sets. Okay. Basically, there are subsets of equations which are soluble by a single, single vector. So I'm going to call each of them soluble sets. So what do you think is the answer for this question? What do you think, what do you think is the smallest K for which any list that passes the checks I just defined has to contain L star?
And choose K.
N choose K. N choose K is certainly an
N
epsilon.
choose N alpha. Sorry.
Say it again.
N choose N alpha.
N choose alpha n. Yeah, that's
It's an
definitely,
upper bound. I mean,
that's clearly an upper bound.
yeah.
That's the number of possible subsets of size alpha n.
Yeah.
And as Praneet's amusement shows, this is a pretty ridiculous bound. It's like, it's giving us nothing, right? Like it's just saying try all possible subsets of alpha n, construct this exponential size list in n, and that's gonna contain everything you want. That's not good enough for us. Um, uh, so I don't actually know how to construct an example where this can happen, but I can construct a very simple example where at least exponential in D candidates are provably needed for this particular algorithm to work. I think it can be made better, but I'm gonna just give you this example. This is pretty bad too, right? Like this is not exponential in n, it's exponential in the dimension. Good. So what's the idea? The idea is very simple. Here's the construction. So proof, I guess, proof for this, whatever. Okay. So my good part is simply gonna be the following. Okay. My good part is gonna be so I will have equal number of equations. Okay, for each of the D standard basis vectors. So EIs are simply 1 0 0 0 and like 0 1 0 0 and so on. Okay. So my Xi's in the good part are simply going to be, these standard basis vectors. And my L star is going to be, let's begin with this L star, 1 over square root D times all ones vector. So I'm just like, 1 over root D is just to scale them all down, so that they behave like unit vectors. Okay, this is just to fix norms. Okay, so that's my good part. Okay. So in other words, how does it look? So for E1, if I evaluate L star dot E1, I'm going to get 1 over root D. At E2, I'm also going to get 1 over root D. At ED, I'm also going to get 1 over root D. Okay. I hope this is all simple and clear. And now, I have to, here comes the adversary. The adversary can look at this good set and come up with, this bad set however they want. So here is my bad set. My bad set is also going to contain an equal number of E1, E2, EDs for X's. Okay. And for each E1, like, so for each of the time that E1 appears, half the times I would contain plus 1 over root D, and half the times I will have minus 1 over root D for each of these. Okay. And why is this a good idea? Why is this creating a very bad solution, very bad situation for us? Well, I claim that you can, if n is large enough as a function of the dimension, then no matter what vector you want, no matter what plus minus 1 up to this root D scaling vector you want, you can create it as a solution here. Okay, so how do I do it? So let's say that you have a vector plus 1 over root D, minus 1 over root D, plus 1 over root D, minus 1 over root D, and so on, right? Take an arbitrary vector like this, which is not a solution. I am going to find a alpha n size soluble set, which is solved by this vector. What would I do? Well, I look at the first coordinate, right? The first coordinate is also, what this vector would label, whenever E1 appears. Okay, so I'm going to choose some of these. I'm going to choose some of these because the first one is 1 over root D. The second one is minus 1 over root D. So, I'll choose some of the E2 labeled by minus 1 over root Ds and so on, right? And now the point is that if n is large enough, then, for any vector like this, I will be able to construct an alpha n size soluble set. Okay. In other words, I've basically constructed a sample, a set of equations where every Boolean vector, up to this 1 over root D scaling, and there are 2 to the D of them, every Boolean vector is a solution. So I'm going to make that observation. And so, if all I know is that the list contains k solutions with potential, which can, with, associated soluble sets, then I can't quite guarantee that my vector, which is all 1 over square root d's, is going to be contained in it, as long as I don't have a list of size at least 2 to the d. Because I can construct lists that do not contain 1 over root, like plus 1 over root d for all coordinates. I can construct list of size 2 to the d minus 1, which do not contain my vector. So need k at least 2 to the d. Now, one could be wondering that, if I don't want to get my vector exactly, I'm just interested in getting it approximately. Even then, the set of Boolean vectors, even if you like take only set of vectors which are all like somewhat far from each other in any notion of distance, they're still going to be, exponential. Maybe the 2 to the d will change 2 to the d over 100, but it doesn't really make a difference. So, even if you wanted vectors which are like, let's say 0.1 d having distance apart, there's still going to be 2 to the omega d different vectors. So it's not like you're getting in trouble here because of trying to exactly construct trying to construct a list that exactly contains, L star. Even if you relax your goal to containing something only close to L star, you're still going to be in just as much trouble. Okay. So let me stop and see if there are any questions. Is this example clear? It's a very silly, simple example, but it shows you that, this problem at its generality is completely insoluble.
Pravesh, so
Yeah.
in this example, our n will be 2d, right?
Yeah, I think n. So I think you need, okay, so in order for you to create many alpha n size soluble sets, you should take, 2 over alpha copies of each EI. So think of alpha as like 0.1, and then, construct like 20 copies of E1, 20 copies of E2, and so on. Does that make sense?
But they can only take plus or minus 1 over root d, the y's.
The y's can only take, yeah, in this construction, the y's can only be plus or minus 1 over root d's.
Right.
So in other words, like you can even forget about good and bad set. Like this example is simply saying, construct the following subset of equations. Output E1, some O of 1 over alpha times. So it's like, take O of 1 over alpha copies of E1, O of 1 over alpha copies of E2, and so on. And for half the copies, label them by 1 over root d. For other half, label them by 1 over root minus 1 over root d, and so on. And now, if I want to construct a alpha size set for any potential labeling, I'll just pick one equation out of each, right? Like if let's say I have exactly, so let's say, I have, okay, what should I do? Maybe 2 over alpha is enough. So, if I want to construct an alpha size set, I just take, one of the equations from each of these, copies of EI. And I can construct any vector I like. Make sense?
Yeah,
I can make any vector pretend like solution.
Right. Yeah, I guess my confusion is that every Boolean vector actually will satisfy half of the equations, right?
Yeah, and therefore it is very easy to. Therefore, it's very. Oh, not half of the. Why do you say half? Every Boolean vector will satisfy at least alpha fraction of the equations. I don't see a way to prove it half.
Because the 2 over alpha copies, for there are many copies, but half of them like 1 over alpha of them will be identical.
Oh yeah, you're right. I guess I am proving half, so it's even better. Okay, you're right. Yes. So yes, you're absolutely right. Yes, every Boolean vector satisfies half of the equations I have. In particular, I can construct if alpha is strictly less than half, then I can construct a soluble set for every Boolean vector.
Okay. Yeah.
So that's a bad example, right? Like it means that if you give me, like there is a way to give you a list of size 2 to the d minus 1 that doesn't include your favorite vector, the L star, which means that, unless you have a list of size at least 2 to the d, you can't be sure that you've gotten everything.
Yeah, okay, that makes sense.
Okay, good.
Thanks.
All right. So that was a complete failure. But let's examine our failure because we're going to learn from it. The first observation is that for creating this example, actually, even though we pretended like it mattered what the good part is, the good part actually did not matter at all. Why? Well, imagine that the good part is whatever distribution you want. I don't care, okay? Just completely ignore it. You can still create all of this, like you can create all possible Boolean vector solutions if I simply choose the 1 minus alpha n bad equations in the way that I just described. Because I don't have to choose this alpha n copies that contain like any equation of the good part at all. I can simply play this complete game inside the bad part. And so in some sense, this particular strategy, this particular test fails no matter what the good part is. It's like as because I can because I've created the bad part in a way that has exponentially many potential solutions. And so even without looking at the good part, no matter what it is, you have to use a list of size exponential in the dimension in order to make sense here. Okay, so if this was all we could do, it not only precludes the good part that we have, like the construction of the good part that we used here, it actually will eliminate all possible good parts. It would actually make the problem impossible. Of course, that's not true, which means that the test we are using here is also not the right one. Okay, so hopefully you understand this point. No matter what G is, B itself has alpha n size soluble sets for all Boolean vectors. And so like the good part didn't play any role at all. So the adversary can simply do this regardless of what your good part is, and we are in trouble. Good. So we've got to modify our test, right? If we have any hope even for succeeding for some good enough good parts, we've got to modify our test. This cannot be our test. And what is the thing that failed here? Like somehow one thing that we absolutely have to ensure is that the adversary, the prover, should not be able to play this game of constructing soluble sets and giving us equations only from the bad part. Like somehow we must force the prover to give a soluble set that at least intersects the good part. I mean, ideally, we would like him to give us the good part itself. We don't quite know how we could ever check that. But at the very least, we should demand that, the prover should not be able to play this game completely in the bad part. So there should be a way for, them to give us something and for us to check, that the good part is not ignored, that somehow at least some soluble set contains some equations from, the good part, right? Still with me? Feel free to ask questions if I'm confusing you. I'm supposed to be saying everything. Everything is supposed to be relatively simple. Let's see. Good. So how can we do that? So let's do the following. So here's a second idea. Force the prover to give us a soluble partition. What does that mean? Well, this time we're going to demand that the prover gives us S1, S2, so on up to Sk, such that these sets are pairwise disjoint. So, Si intersect Sj is empty whenever, I doesn't equal j. And, their union equals S. So it's a partition of the samples. And each Si should be of size alpha n. Okay. So we will ask the prover to give us a soluble partition. And the soluble part means that, each Si is a subset of equations which are satisfied by some vector. So let's say S1 is satisfied by L1, S2 is satisfied by L2, and Sk is satisfied by Lk. Okay. So in particular, notice that K is clearly at most 1 over alpha. That's good. We like that. And the list, and the list itself is just simply L1, L2, Lk. Before going ahead, just to make sure that you're all following me, can you tell me why this idea is, well, immediately bogus? Why can I not force the prover to give me this?
There may not exist such a partition.
Exactly. There is no reason that, the adversary would try to play nice with you and try to create a situation where, there is a way to partition the whole input sample into soluble sets. Let's ignore that for a bit, okay? Let's imagine what happens if the prover can give us this, okay? There is, of course, an issue that such a thing may not be even possible for the prover. Even for the all-powerful prover, they may not be able to give us such a partition. In that case, we'll do something else. But let's imagine that we get lucky, at least in the kind of examples we were looking at right now, there was a soluble partition, right? And so, we'll ask, prover, please give us a soluble partition. Each set should be, of alpha n size. This time, you can't make any of the sets intersect, okay? And give us like 1 over alpha sets. And so now what have we ensured? Why does this partition somehow help? Well, here is a observation. There must exist an I such that Si intersect the good part is at least alpha fraction of the good part. Why? It's pigeonhole principle, right? This S1 through Sk is a partition of all the points, right? G is some set. So G's points are spread out across S1 through Sk. And so one of the sets must contain at least 1 over k fraction of the points. So this alpha is simply 1 over k. So this time we have, if we can force the prover to give us a soluble partition, we've certainly, gotten to a state where at least one of the soluble sets has to contain some equations from the good parts. We again don't know which, right? We're trying to play this game in a way that, doesn't try to use the knowledge of G, but we can still somehow, convince ourselves that, well, there is some Si in this list which intersects the good part. Okay? Still good? So now, at least because the game is not being played only in the bad part, because the game at least has some relationship to the good part, we can hope that, there is some, so there is some hope that, the information about L star would be in the, list presented to us. So we can ask question, does this mean that L star is in the list given to us? Well, let's examine, right? We know there is an SI that intersects G in not just some equations, but in fact, alpha fraction of the equation, just a constant fraction of the equations, right? So let's look at Li. So Li is, the equation that correctly labels, Li is the vector that correctly labels all the equations in Si, right? And Si intersects G in non-trivial fraction of the equations. So the best hope that we have of finding L star is to simply, Li itself be close to L star, right? Because Li, labels Si and Si intersects G appreciably. So that's our hope. So let's see, whether that hope pans out. Now, in the subset Si intersect the good part, so we know that L star, labels all the equations in G correctly. We know that Li labels all the equations in Si correctly, which means that if I look at the intersection, both Li and L star label all equations correctly. In other words, they satisfy all the equations in this alpha times size of G number of equations, right? Both Li and L star must satisfy them. And so our hope is that, this should mean that Li should be equal to L star. So when does that not happen? Let's see, so let's see what happens if Li doesn't equal L star despite this. Well, it means that if I now look at the equations, it means that for every xj, yj in Si intersect G, it must be true that Li dot xj equals L star dot xj, but Li doesn't equal L star. It means that Li minus L star is a non-zero vector that is orthogonal to X star, right? So from here, I want to derive. So it means, so conclusion, there's an alpha fraction of G such that there is a vector, there's a non-zero vector orthogonal to all the equations in this alpha fraction. And now, we want to say that this should not happen. Okay, this is not a reasonable thing to happen. If this does not happen, then we are good, because then Li must equal L star, and then we have a list that contains L star. So let's just rule it out by fiat. Okay, let's just say that this does not happen. Okay, and you'll see that we are doing something which is less arbitrary than it might appear, because we are going to give this a name and then discuss why it's a interesting thing to enforce. Okay, so let's define this key property. We kind of saw this property in one of the proofs the last time, but this time, we are going to play with it in somewhat more detail. Okay, so we're going to say that a RD valued random variable, let's without loss of generality force it to always have mean 0, is said to be delta anti-concentrated if for all directions v not equal to 0, probability that y projects to 0 in direction v is strictly less than delta. Okay, so the chance that in any direction, so given the direction, the chance that y projects to 0 in that direction is less than this number delta. If that happens, I'm going to call it delta anti-concentrated. Okay. I want to extend this definition to subsets because that's what we deal with. So I'm going to call a subset T of RD is said to be delta anti-concentrated if uniform distribution on T is delta anti-concentrated. Okay, and now notice that this is the right property. This is the property that we were talking about, is that if the good part is delta anti-concentrated for delta equals alpha, then in the above argument Li must equal L star. Okay, let's go back and check that the parameters are correct. What have we concluded? We've concluded that this happens for the intersection of Si and G. Si and G intersect in alpha fraction of the points in the good part, right? So if I look at the set G, then on an alpha fraction of the points in set G, Li minus L star is a vector that projects to 0. Okay. Now I'm saying if we knew in addition that G is delta anti-concentrated for delta equals alpha, then I know that in any non-zero direction, the chance that, in any non-zero direction, the fraction of points, that project to zero in that direction from G is strictly less than alpha. Okay. Here we have found a vector where so this vector Li minus L star that projects to zero on at least an alpha fraction of the points. Well, that's a contradiction unless Li equals L star. In other words, Li minus L star is the zero vector. Okay. So I want to observe that if we knew that G is delta anti-concentrated for delta set to exactly alpha, then in fact, Li must equal L star. It means that soluble partition, let's see, maybe say it this way. A list with a soluble partition as a certificate always contains L star. Okay, let's pause for 30 seconds and make sure that we are still on the same page. Still with me? All I've done is like I've basically given up on my worries by simply making a definition that makes my job possible, right? That's all I did. And I just gave it a nice name. We'll see reasons to discuss, to give this name and etc. in a second. But at least the facts of the matter should be clear to you that if G is alpha anti-concentrated, then in fact, if I can give you a list along with a proof which is a soluble partition, then that list must contain L star. So yeah, ask away any questions that you might have.
So we are assuming that n is at least d over alpha squared, right?
Right. Okay. So I should maybe clarify this. I'm not going to be concerned about n which is small here. I'm always going to be like, my algorithm will work for n which is large enough.
Okay.
So you're right. Yes, n is always going to be at least d over alpha square or something. Yes.
Does delta anti-concentration appear elsewhere, or is it tailor-made for this problem?
Good. Yeah, we're going to come to that. Yes.
Okay.
So anti-concentration is a very well-studied property. Anti-concentration, is well-studied. So we saw, one example of a very anti-concentrated distribution the last time. So let maybe, and actually very interesting property. So let's talk about that a little bit. So let's say that I have a Gaussian random variable. Let's maybe talk about random variables first, and then we'll come to sets in a second. Okay. So let's say, y is the standard Gaussian in d dimensions. Okay. What's the chance that yv is 0? V is any non-zero vector. What's the chance?
Zero.
Right. Okay. So this, I know I'll annoy many analysts and probability theorists by writing this statement, but in general, like there is no way to in fact even define the probability of yv equals 0. But if, for example, I had to clear my name, I would say probability that yv is less than delta is less than delta. And then I just like send delta to 0. Take limits as delta goes to 0, for example. Okay. So this is great, right? This is the property, by the way, that we used the last time. So one example of a distribution that we already know satisfies this property is the standard Gaussian distribution. Well, not just the standard Gaussian distribution, but even uniform distribution on a large enough sample from a Gaussian will also satisfy this. So there is also a claim. So okay, maybe I should say then y is 0 anti-concentrated. It's a pretty awkward expression, but that's what it is. That's what it is. Now, let's say that I have y1 through yn, IID samples. I don't exactly remember what constant I should use, but let's say n is bigger than 100d, some big constant times d. Okay. Then Or maybe I should have, okay, I think I should have 100 d over delta. Then the set y is also delta anti-concentrated. In other words, so this is a slightly different statement and slightly more useful statement to us, because it's not talking about a infinite support random variable. It's talking about some large enough sample from the same random variable. It's saying that if I take 100 d over delta samples, then the chance that there is some direction, arbitrary direction, along which delta fraction of the points yi's project to zero is basically very, very small. So let's say with probability at least 99%. And this again, I'm not going to prove this, but this is like simple exercise in Chernoff plus union bound. Maybe not, maybe some care is required because okay, let me not get into it. But here the set you're union bounding kind of depends on n itself. So it's a slightly tricky union bound, but still works out fine. Okay, so I'm just going to say that this is a Hoeffding plus union bound argument. And so this is kind of interesting because what we found is not only is the Gaussian distribution, which is an infinite support random variable, anti-concentrated, it's actually this property is inherited by some d over delta up to constant size sample from a Gaussian with reasonably high probability. So it's not such an unnatural property. It's it holds for large enough samples from a Gaussian distribution. Okay. Now there are like actually many distributions which are anti-concentrated, and this is a well-studied property. We know, for example, that a certain amount of anti-concentration holds for polynomials of Gaussians, which are not usually, and so there's this famous inequality called as the Carberry-Wright inequality. It shows that polynomials of Gaussians are also anti-concentrated. And then there are like non-trivial theorems in convex geometry that show that log concave distributions in general, which is like a large class of distributions, also have certain amount of dimension independent anti-concentration. And so, we'll not get into this. There are many distributions that satisfy this property. We're happy with the fact that one distribution satisfies it because it makes what we're going to do today non-vacuous. Okay, so that's all I'll say about this. But I guess one important thing to notice is that this is also not there are like very natural distributions that you can imagine which are not anti-concentrated. So it's also good to see examples of distributions which do not satisfy this property. Okay, so here is a distribution. Let's say, so let's see, did I say this correct? Okay, good. So this is example one. Okay, B, uniform distribution on the Boolean hypercube. Okay, distribution that we usually like very much is not half anti-concentrated. Actually, it turns out that half is the optimal constant here, but is half minus beta anti-concentrated for every beta bigger than 0. Okay, so what does that mean? It means that there is a direction along which if I project the distribution, then it takes the value 0 with probability half. It's very simple to actually produce such a direction. It's simply one of the standard basis vectors. Okay, then notice that if I take an x, which is uniformly distributed on 0, 1 to the n, then x dot ei is simply, its ith coordinate, and it's going to be 0 half the times. And so there's no surprise that, uniform distribution of the Boolean hypercube is not anti-concentrated. And actually, more generally, discrete distributions, have this problem. So, you can look at maybe this distribution. Uniform distribution, let's say, on this set is not 1 over q anti-concentrated. And it's the same issue, right? Like if I take any coordinate, then it's going to be 0 about 1 over q fraction of the times. Now, actually, you could, if you are insightful here, you might wonder that, oh, it seems like really it's a problem with these special vectors, standard basis vectors. Okay. And people have wondered about this question about at least 100 years, for at least 100 years. So this question was, first asked about, non-trivial anti-concentration properties of, the uniform distribution or discrete distributions, uniform distribution of discrete sets like 0, 1 to the n. And in particular, Littlewood offered, etc. And so the earliest result here is Littlewood offered. It was generalized by Erdős, and there are like many works, in modern mathematics that try to establish properties that say that, if you ignore vectors that satisfy some non-trivial structure, then everything else, if okay, so maybe say it this way, the distribution may not be anti-concentrated only if I project to one of the structured directions. So, this EI, etc., are very structured directions. They are in particular very sparse vectors. And this Littlewood offer type theorems, basically identify some structure and then say that, as long as you take a vector which is not of the structure, your distribution is going to be anti-concentrated, when projected to non-structured directions. And in particular, as you can imagine, if I take a vector v, which satisfies the following property, that any coordinate is, let's say, at most beta fraction of its L2 norm. So no one coordinate dominates, is, I forget the constant, but, is like omega beta anti-concentrated. So maybe the way to think about it is that if I look at probability that xv is 0 is at most omega beta. And so, it's really like some property about sparse vectors. If I take like dense enough vectors, if I take vectors where no single coordinate dominates too much, then in fact, even the hypercube turns out to be a reasonable distribution, but it's not anti-concentrated in all possible directions, unfortunately. Okay, good. Okay, now, we kind of pulled anti-concentration out of our hat in some sense, right? Like we were looking at this special kind of certificates for whatever reason. We came to it and then we said, hey, you know what? Let's just make this property be satisfied by our set G, and everything should be okay. But it turns out that this property is, in a certain sense, necessary. And so let me maybe quote this proposition. It turns out that there exists a good set where xi's are distributed uniformly on 0, 1 to the n, such that List-decodable, noisy linear equation problem is impossible to solve. So I'm being somewhat informal, but what I'm saying is that, not only is this anti-concentration property kind of a nice thing for us, but in fact, if your distribution does not satisfy it, if your good set does not satisfy it, then in fact, no algorithm can win. And in particular, if you try to do this list-decodable noisy linear equation solving on the hypercube, you're going to fail. I actually had planned to give you this full proof, but I'm a little bit behind the schedule. So I'm going to ignore this. And it's really, really simple. It's like a 10-minute thing. And so, I will point you to where the proof appears at the end of the lecture. Okay. So right now, just take my word for it that, it turns out that for this one distribution, actually, also the generalization to this Q-ary discrete cube, etc., you can construct simple examples which prove that it is information theoretically not possible to calculate a list whose size does not depend on the dimension. So, any list has to have a size that grows with the dimension if you want to solve the list-decodable noisy linear equation problem, for good sets where xi's come from one of these discrete distributions. And so, you can think of this proposition as saying that, hey, you know what, anti-concentration is not only something that we pulled out of our hats, but also kind of looks necessary. Okay, so, okay, good. So very good. Okay, good. So what have we done so far? So let's take stock of where we are. So we saw that soluble sets are not enough as certificates. Soluble partitions are enough, for all good sets that are, alpha anti-concentrated. But we are not kind of done. We are still in this certificate land, and of course we are not done for algorithm by a long shot. But we are also not done in our task of building a certificate here, finding a certificate of certifying algorithm, because soluble partitions need not exist, as we observed earlier. So what this means is that if somebody is able to find such a certificate for us, well, great. Then we are happy. Then we do have a good list. We are sure of that. Given that G is sufficiently anti-concentrated. But such a partition did not exist. So we haven't really solved the problem for all possible G's and B's. Even when G's are anti-concentrated. So let's try to generalize. Let's generalize soluble partitions to get a notion of certificate for true solutions that exists for all alpha anti-concentrated G's. Okay, good. So how are we going to do that? So we are first going to so let's go back and observe why this soluble partition works so well for us. Okay, so why did soluble partition work? Well, remember, the reason we came up with it was because we were worried that the soluble sets were playing the game outside of the good set. And so we wanted, somehow that the certificate should give us a soluble set which intersects the good set in appreciable number of points, right? Of course, because we don't know where the good set is, the only way to ensure this was to somehow, say that each equation in my set should be contained in some solution set. That's how we actually make this happen, right? And so, the first property that really we wanted from the soluble partition was coverage. If every equation in the input sample, in the input is, part of some solution set. Good. And now, this alone is, of course, not enough. If I give you very tiny soluble sets, then, it won't really imply appreciable intersection with good part. And so the other part we really used crucially was that each soluble set in my partition is large. Okay. So now we will, try to keep these two properties and try to generalize a certificate so that it exists for all G's. Okay. So the idea is to view a partition, a soluble partition, as a probability distribution over subsets of the equations. Okay. And the distribution, so I'm going to think of a partition as a distribution over subsets of n, and the subsets will be of size at least alpha n. So in a particular, if I have a partition, so for example, if I have a partition S1 up to Sk, then I'm thinking of this as a uniform distribution on, the set S1 through Sk. So, like with probability 1 over k, I would put the set Si. okay, for any I. That's the distribution I'm thinking about. And so I'm going to view, so you'll see in a second why am I doing this, but I'm just going to view a partition as simply giving me a distribution over subsets of all possible equations, such that each subset in my support of my distribution is of size at least alpha n, okay? And each subset should be soluble, as in there should be some vector that correctly solves the linear equations in that subset. So we're going to view our partition as that, as slightly more generally as a distribution on, alpha n size subsets, each of which is soluble. Okay. So now if I look at it as a distribution, let's call this distribution mu. Okay. Now mu is this distribution. The largeness property is kind of satisfied by, just baking it in, right? Because we made the support of this distribution be on sets of size at least alpha n. The largeness property is just like, trivially satisfied, right? In order to force coverage, so now we want to force coverage. That is the fact that every equation, is covered in one of the sets in the partition. This is the property we want to, somehow capture. Like we want to now phrase as a property of the distribution mu. Now, you would agree that in a partition, if I now compute the following probability, so the probability, so I have a distribution on subsets. So if I sample a subset, let's say Si from mu, and then compute the probability that some sample, let's maybe be more descriptive, xj, yj is included in Si, then for a soluble partition, this probability is exactly equal to what? Because I've been speaking for a long time and I'm not sure if all of you are with me. What is this property? Like if mu is the uniform distribution on the sets in the partition, what is this probability? What is the chance that a given sample xj, yj lies inside a, a subset Si picked according to mu?
1/k.
1/k, exactly. Right, because they're exactly k sets. All of them are of size exactly equal to alpha n. And we're going to assume that 1 over alpha is an integer for now. And so, what this is, this is simply saying that, xj, yj appears in exactly one of those sets, which means that, it's going to be contained in Si only when I pick exactly one out of the k possible sets. The distribution on them is uniform. So this probability is exactly equal to 1/k, which is equal to alpha, right? Still with me? Okay, so let's, call this event by the name wj. Okay, we'll say that wj is 1 if, so okay, in other words, what do I mean? So, equivalently, mu is a distribution on w. Now w is a vector, in 0, 1 to the n. Think of it as like describing which, it's the indicator of the set S that lies in the support of mu. So, instead of saying that mu outputs a set, I'm going to output the indicator vector of that set. That's a vector, in 0, 1 to the n. And it satisfies that sum over wi is exactly equal to alpha n, right? And this property here, so remember, like observe that, this is simply, what's the chance that wj is equal to 1, right? So the probability that wj equals 1/k is equivalent to saying that expectation of wi for every I equals alpha. Okay, so far I've done nothing. I've translated things, but I want to pause and see if everything is clear to you.
So I had a question about stuff, but it's a little bit earlier.
Sure, yeah, let's do that.
So like when we first introduced this problem, it seemed that we were like deterministically defining like what the good set is that's
Yes.
Embedded among all these things. But then we started talking about like anti-concentration of this set.
Yes.
And in particular, like, if you know that a large fraction of the set is in one of the soluble sets that you force the prover to give you back. But then I don't understand how exactly we make this move from like if the good set is anti-concentrated, then with reasonable probability we know that
so there is no, so let's
yeah.
understand, right? Like there is no probability once the good set itself is anti-concentrated. There is nothing probabilistic. The statement that G is anti-concentrated is not a probabilistic statement. Let's go back and check the definition. So if you're asking a good question, so let's go back and check. So a random variable is anti-concentrated if, in every direction V, the chance that Y dot V is 0 is less than delta, okay? That's something probabilistic, right? It's some property of a random variable. But now let's look at, when is a subset anti-concentrated? So here, when is a subset of, points in RD anti-concentrated? Well, I'm going to call a subset anti-concentrated if the uniform distribution on T is delta anti-concentrated. Notice that even though the definition, is talking about a certain random variable, namely the uniform random variable on T, this property itself is a completely deterministic property of the set T. There is nothing probabilistic about it. Alice, does it make sense?
Yeah. So this part is fine for me.
Okay.
It's more the next step. Yeah.
So yeah, the next. What do you mean next step?
As in, I don't see like why this property of, or like why the uniform distribution over the good set is anti-concentrated. This allows you to say something about whether or not Li and L star have to be equal.
Okay, good. So we haven't completely proved that yet, but if there is a soluble partition, so what did we really prove? We proved that imagine that G is delta anti-concentrated for delta equals alpha. Okay. Then we said, imagine that the prover gives us a soluble partition as a certificate of correctness for the list they are suggesting is a good list. Then I claim that we did establish that one of the LIs must be equal to L star. And let's go back and check. So we were a bit quick and we're introducing several ideas. So let's be a little bit careful and make sure that we understand this. So how did we argue this? We said, hey, you know what? By pigeonhole principle, there must be one of the SIs in the soluble partition, which intersects the good set in, alpha fraction of the points of the good set. You still with me on this? Good. So now we look at, this intersection SI intersect G. We observe that because Li solves all the equations in SI and L star solves all the equations in G, on the intersection, both Li and L star solve all the equations, right? In particular, that must mean that for all xj, such that xj comma yj is in SI intersect G, Li dot xj should equal L star dot xj.
Yep.
So what that means is that Li minus L star inner product with xj is 0. And now, I'm observing the following. I'm saying, hey, you know what? For contradiction's sake, imagine that Li minus L star is non-zero. In other words, Li is not equal to L star. Then Li minus L star is a non-zero vector, right? And the property that, sorry, something bad happened on my computer screen. Sorry. The property that if you project the points in the good set G, if you project the points in the good set G along the direction Li minus L star, then an alpha fraction of them becomes 0. This means that the uniform distribution on G is not alpha anti-concentrated unless Li minus L star is 0. Because, an alpha fraction of the points in G are projecting to 0 along this direction. And so the only resolution if G is alpha anti-concentrated is that Li minus L star must be 0. In other words, Li equals L star.
I see. Okay. I see what I did not understand before. Thank you.
Okay. No, but this is important. It's true that I did a bait and switch on you. I brought in distributions even though there was no distributions. But in my defense, the property that we are using about G is completely deterministic. There is nothing probabilistic about it. The reason I argued about distributions, etc., is to show you that there are at least it's like this property is not vacuous. This would be a pretty bogus property if it does not hold for any set G. But I wanted to prove to you that not only is this property good, it's actually non-vacuous. Like there are sets which are anti-concentrated. In fact, I wanted to prove that there are sets which are not too large which are anti-concentrated. And I wanted to prove, in fact, that these sets are not like some archaic sets. They can be generated by just uniformly sampling from nice distributions like Gaussians. Okay, so the distributions part only occurred to buttress my argument that I'm not giving you a vacuous or a bogus condition. It's a non-trivial, but not relatively simply satisfied condition. Do I justify myself? Did I justify myself? Okay, perfect. Good. So, okay, very good. So I hope, things are clear now. Very good. So, okay, so now, let me come back and see if there are any questions about this translation of notation that we did. What we did was we took a partition, we just, for whatever reason, we reinterpreted it as, the uniform distribution on the sets in the partition. You'll see what I'm doing this, right? You'll soon see, why this was a legit thing to do. But right now, just like bear with me and carry on. So what are we saying? Hey, you know what? Now let's look at the two properties that really were relevant in this argument that we just did and went over again, right? The two properties that were relevant were that, every point is somehow covered. This allowed us to do pigeonhole principle and argue that, G must intersect one of the SIs in alpha fraction. And then, the reason that we could argue that it must intersect in alpha fraction was that every set was large, which allowed us to conclude that there are not that many sets, right? So we used somehow both these properties, coverage and largeness. We want to now, phrase them as properties of the distribution that for whatever reason we want to, think about in the context of this partition. Said, okay, let's look at the uniform distribution on SIs. First, let's do a change of notation and think of the distribution as just like, on vectors in 0, 1 to the n, where, vectors in 0, 1 to the n are supposed to be the indicator, vectors for subsets of, the n equations, right? And then the fact that each set was large is some wi is alpha n. The fact that we had uniform coverage of all the points is basically that the expectation of each wi is alpha. Each I is chosen alpha fraction of the times. Okay, so all I've done so far is translate the properties that we use from a soluble partition, into this distribution lingo. Still good? So far so good? Okay, very good. So now, so the key point is that such a soluble partition may not exist, right? Like this is what we were struggling with. That's why we generalized this. So we now have to, talk about a generalization of a soluble partition that, somehow always exists. So here is my generalization. So I'm going to call it maximal coverage partition or maximal coverage distribution. Mu on W satisfying, let's call this property 1. Satisfying 1 is said to be maximal coverage if E mu Wi square is minimized over all mu supported on soluble sets. Okay, so now I'm saying I can't quite find a partition, but I'm going to do the best possible thing. Okay, so the intuition is that uniform coverage means that each point occurs only like about alpha fraction of the times. Okay, now this was exactly satisfied when I had a partition, but I may not have a partition. Okay, so what I'm going to do instead is try to minimize the sum of the squares of Wi, sum of the squares of expectations of Wi. Okay, notice that, if I had no constraints, sorry, let me maybe try to be more clear. Notice that if I look at expectation of the sum, right, then sum Wi equals alpha n, because that's a constraint that that's what the every point in the support of mu satisfies. So sum over I of mu I has to be alpha n. Given this, and like wi's are supposed to be 0, 1, valued. So given this constraint, notice that if I had no other constraints and I didn't want to pick soluble sets, then the best thing you can do to minimize some of the squares of expectations of wi is the way to think about it is like if I have L1 constraints on a vector, then the L2 norm is minimized when you spread out the mass. Okay, so under no other, so maybe say this way, under no other constraints, E mu wi square is minimized when all of these numbers are equal. And if all of these numbers are equal and their sum has to be equal to alpha n, then notice that there are n such numbers, so each number should be alpha. Right? If I sum alpha over n numbers, I get alpha n. So if I had no other constraints, I'll set them to just be equal, which is equal to alpha n, which remember is what the partition satisfied. So you're saying, hey, you know what? If there were no constraints, then I would actually have set this to alpha. But of course, I have constraints. In other words, each point in my support has to be a soluble set. And so I may not actually end up with alpha, but my hope is that this still gives me this maximal coverage property, that somehow I can still argue that any distribution that is maximal in its coverage does intersect appreciably, with the good set G. Does the definition make sense? Still good? And so now, this is an object that always exists, right? Like it is defined as a solution of an optimization problem. So there is no problem with its existence. I'm going to just like say, find me a distribution, supported on W's that satisfy some Wi equals alpha n, W in the hypercube, and something that minimizes sum over I of E of Wi squared. Okay, notice that this is actually, by the way, equal to the L2 norm of expectation W. Okay, they're saying find me such a distribution that minimizes this. Such a distribution always exists. Like I'm going. Oh, actually, let me ask that. Okay, I'm claiming it, but I haven't really argued it. It also gives me a pause. So why is in order to argue that such a distribution, such a definition is always well defined for all G, I have to show that at least one distribution exists on the soluble sets. Why is there such a distribution? Why is this definition not vacuous for any G? Well, notice that I can simply choose mu to be, the single point distribution that outputs the good set G, right? That's clearly one soluble set. So there is at least one soluble set of size alpha n in my input set of equations. So such that like I'm not optimizing over an empty set of distributions here. And because my optimization, like this minimization of this L2 square norm of EW is happening over a non-empty set, it's, the output of it is well defined. Still with me? Good, very good. So now let's make it come to fruition for us. Let's make sure that this property actually gets us what we wanted. Okay. Okay, so here we are. Claim, suppose mu is a maximal coverage distribution over soluble subsets of n of size alpha n. Actually, let's make it exactly equal. Just makes arguments cleaner. Okay. Then, so now I want to say that any such distribution must in fact have appreciable intersection with the true good set, right? So here is my claim about that. Then expectation of I in G, Wi. So I'm kind of, slightly abusing the notation for you. I call goods a set of equations, but now I'm using it as indices. Okay, pardon me, because otherwise I have to introduce new notation. This is just cleaner this way. So sum Wi I in G, this is basically, the fraction of, so if I output a set, this is basically equal to the intersection with G, right? So notice that this is simply, S mu S intersect G. That's what this expression is. Okay. So the claim is that this is at least alpha times G. Exactly the same property that held true for a soluble partition. Okay, so what we're now saying is that, hey, you know what? The same role is going to be served by a maximal coverage distribution, at least in expectation. Okay, good. So, okay, so this is, okay, let's see, what should I tend to do? Okay, let's do a proof. I was debating whether it's good to do a proof or not. So I will be somewhat sketchy, but at least I will give enough of a intuition why this is supposed to be true. Okay, so what's the idea? So let's look at, so let's define this. Let's call this weight of G as this quantity. Actually, let's make it this. So this, you should interpret as fraction of W that intersects with G. Okay, we are trying to prove that expectation of weight of G, oh, actually, let's in fact take expectations right here, and there is no pseudo yet. Okay, so this is expected fraction of W that intersects with G, right? Now we are trying to prove that this has to be, so our goal is to prove that weight of G is is at least alpha. So how are we going to show this? We have so notice that we have no, like, the algorithm or us has no idea of what G is, right? So what's the only way I can show? I have to use the fact that mu was supposed to be maximal, right? That's the only thing I have in my control. So I want to say that if this does not happen, then mu must not be maximal. That's the only thing in my control here, right? So what we will show, if weight of G is less than alpha, then there's another distribution. Let's call it mu prime, such that E mu prime W is strictly smaller than E mu W. In other words, I can decrease the objective, which is a contradiction because I was supposed to be optimal already, right? So if I do this, then so this proves that weight of G must be at least alpha in mu. Okay, and what's the idea? What's the idea for doing this? How would we, this is something that, this is the kind of argument that you must have done at least some point in your life. So the way to do it is, if weight of G, so idea to, so we'll construct mu. And how will we construct mu prime? Well, we'll say, for some lambda, consider mu prime equals 1 minus lambda mu, meaning we are going to mix, a little bit of a different solution with mu. We're going to say that, I'm going to find a different solution by perturbing mu. Okay, that's what we're going to do. So, I'm going to write down this distribution and then explain to you what it means. So let mu star be the following distribution. It simply outputs the good set all the time. Okay, output G with probability 1. That's mu star. Okay, so now what does this definition mean? This means that with probability 1 minus lambda, output a sample from mu. And with probability lambda, output a sample from mu star. Okay, so I'm, I'm mixing mu with mu star, and this is a legit thing to do because mu star is definitely a solution. Mu star is definitely a distribution that satisfies all the properties I want. It is supported on an alpha S size set. It is supported on a set that is soluble, right? So mu star certainly is a feasible distribution for the optimization problem, right? So it is, and because mu star is feasible, mu is feasible, this mixture of them is also feasible. It's also supported on soluble sets of size alpha n. So mu prime is a legit distribution to consider for all possible values of lambda. And I'm going to prove to you that, if it so happens that weight of G under mu is strictly less than alpha, then in fact, by making lambda slightly non-zero, I can in fact, decrease this L2 norm, L2 square norm. Okay. Now the thing to observe, all of this is like, okay, the argument itself at the end is very simple. If this is what you decide to do, the thing to think, maybe the thing to wonder about and to see, see what's really happening is that anything that we can check cannot use the knowledge of G. So notice that, what we are minimizing, etc., has no dependence on G. We are simply minimizing the L2 square norm of W with respect to mu, right? But we are trying to guarantee a property of this about this unknown G. Okay, so somehow everything about this, the whole idea here is that somehow, we are trying to argue that something good happens with respect to this unknown set G by forcing, conditions on mu that have nothing to do with G. Okay, that's something, to take away, what we're trying to do here. Okay, good. And so let's see, what's a good thing to do. Okay, in fact, let me not do the rest of the proof right now. Okay, let me just stop here and give you, so I've given you some idea that I can somehow mix and show that there's a non-zero lambda. And at this point, what I'm going to do is like write down an expression for mu prime and, take a derivative with respect to lambda, set lambda to 0 in the derivative and argue that it is, negative. That's what, I'm going to take the derivative of this function as a function of lambda. That's what I'm going to do. That's what I'm going to do to prove that, there is a, if I push mu off towards mu star a little bit, then I can actually gain, right? That's what I'm going to do. Let me not do that technical argument because I'm running a little bit short on time. So we'll come back and do this at the end if there is time, okay? And if not, then I'll point you to again where it appears. Nothing hard is going on. And I think in some sense, at least the intuitive idea I explained to you right now. Okay, so now let's quickly see why a maximally coverage partition kind of serves the same role, and we are done. Okay, and then we'll take a quick break. So let's see. So now suppose the prover gave you this. Now here is one bait and switch that I already did, okay, that you should notice. The partition, the soluble partition thingy was a distribution supported on exactly 1 over alpha things, right? And so the list size were at most 1 over alpha by fiat. When I went to this maximal coverage and when I went to this, the conditions that we enforce on the distribution, we no longer enforce the condition on the size of its support, right? We didn't say that mu prime or mu whatever should be supported only on 1 over alpha sets. So a priori, I don't get a small list, right? Because if I simply output all of the points in the support of mu, that's potentially a large list. But I want to convince you that that's not a problem and that we don't need to explicitly force a support size bound. Okay, so here is a lemma towards that effect. Actually, let me just use this as a lemma so that I don't write again. Very good. Let k equals 20 by alpha minus delta, where okay, sorry about that, and let G be delta anti-concentrated for some delta strictly less than alpha. Okay, so I set this as a bound, and I'm assuming that G is delta anti-concentrated for delta which is like strictly less than alpha. Okay, so now I'm going to prove to you that, actually let me just describe the process. So then let L equals L1 Lk be produced by sampling soluble K IID soluble sets So basically what I'm doing is just take K independent samples from mu. Mu might have a large support, but I'm just going to just take K independent samples from it. And for each of the sets, I'm going to pick some vector that correctly labels each of the equations in that set. It's a soluble set, so there exists one such equation. There is one such vector at the very least, right? And I'm going to just simply return this list of size K. Okay, then L star belongs to L with probability at least 0.99. In other words, I have taken a maximal coverage distribution and I have rounded it to a list of size 20 over alpha minus delta. So if you think of delta as, let's say, alpha by 2, then this is a list of size 40 by alpha. So, okay, we're not at 1 over alpha, but we're not so much worse either. Okay, we are like some constant fraction larger than the optimal bound. And let me quickly do this proof. And this is like, it's a very simple averaging argument, okay? Now, we already know that if let S1 through Sk be the soluble set sampled. Okay. Now we know that expected value of Si intersect G is alpha n for all I. Right, because this is what our distribution mu satisfied. This is the fact that we claimed here. Didn't complete the proof, but at least we claimed, right? We use this fact to conclude that in expectation, each SI intersect G is at least alpha n, right? So all this 20 over alpha minus delta, etc., is happening is just to show that one of the S1 through Sk's must satisfy this property. Okay, so I'm again not going to go into detail, but just claim that then probability that Sj intersect G. So this is still a fact about the distribution. So I'm doing some simple averaging is at least alpha minus delta by 2. Trust me on this calculation. And now so it means that if I fix an SI, then the chance that it has at least alpha plus delta by 2 intersection with G is at least alpha minus delta by 2. Remember, delta is something strictly smaller than alpha. So this is strictly bigger than delta, right? Because alpha is bigger than delta, this alpha plus delta by 2 is bigger than delta. Okay, and so now then probability that at least one so now this is a probability over the sampling of S1 through Sk is bigger than alpha plus delta by 2 times the size of G is at least, this is just this 1 minus alpha minus delta by 2 to 20 over alpha minus delta. And you can convince yourself that that's basically about e to the minus 10. Okay, I'm going to say that that's bigger than 0.99. Anyway, so this argument is really simple. This is just simply saying that if I sample about, constant fraction larger than 1 over alpha size, 1 over alpha IID samples, then one of the sets actually will intersect about as much as what the expectation of the distribution indicated. And then, I can do the same anti-concentration argument. Okay, so I'm not going to maybe do this in too much detail. Like after I'm done, so here, at this point, I can finish the proof because then notice, so, now, say SI is such a set, then, we can do the same argument as before. So, then Li and L star both satisfy all equations in Si intersect G. This is a set of size strictly bigger than delta times size of G, because alpha plus delta by 2 is bigger than size of bigger than delta, and since G is delta anti-concentrated, it means that Li equals L star. Okay, so let me stop here and make a claim and then take a break. So what have we done? We've actually done nothing about algorithms yet, okay? We've worked very hard to show that we found a certificate, okay? So conclusion, we found a certificate that allows us to get a good list of size about O of 1 over alpha whenever G is, let's say, alpha by 2 anti-concentrated. Okay, so good. So so when we return from the break, we'll take a 10-minute break, and then we'll return from the break, and we'll show how to make all of this argument that we did right now work within SOS and get an algorithm. Okay, but as I promised to you earlier that our certificates were kind of natural and our analysis was kind of natural in the previous lectures. We had to work a little bit to get the certificate and the notion of anti-concentration right here. Like one other thing you might notice is that we had to play with the assumptions on the good set while we were constructing certificates. So in fact, this is the interesting part about this whole method of algorithm design. Like you start from basically no priors on what your assumption should be. You play with your certification procedure and let it suggest to you what assumptions you should make. It also, of course, you should go back and check if those assumptions were reasonable, etc. But you kind of saw the whole process in this big thought experiment that we did to arrive at reasonable certification procedure. So now we'll resume at 6:10 and design an efficient algorithm that kind of fits the same bill. Okay, so if most of you / all of you are back, I would again request you to turn on your videos if you can. Again, not mandatory, but great if you can. Okay, good. So let's let's proceed. And we've basically seen in some gory details, and along with a certain somewhat interesting brainstorming process, how to come up with this final idea of a certifiability like a certificate for a list that definitely does allow us to conclude that at least whenever G is sufficiently anti-concentrated, it gives us a small list which is guaranteed to contain a vector L star. Right, and so I mean, maybe we should pause and make sure that this itself is a slightly non-trivial result, right? It's not clear that there is even an exponential time algorithm to find a list that contains it's not immediately a priori clear that given a set of good points which are sufficiently anti-concentrated, it's not clear that you can find a small list that definitely contains L star, right? Like it's not clear that there is any algorithm for this problem at all. And so at this point, we've at least accomplished the existence of a infinite time algorithm, right? Notice that the trivial infinite time algorithm is simply to go over all possible n choose alpha n things, right? So it is trivial to produce a list of size n choose alpha n. But what we've done is something non-trivial. We have produced in infinite time potentially a list of size which is a fixed constant that does not depend on the number of equations or the dimension, anything, right? And so even at this point, we've proven a certain non-trivial result. But now we'll go ahead and actually make it into an algorithm. Okay. So, so far there was the same theme to our algorithms, right? Which is once you have a certificate, you try to design an algorithm that tries to search for that certificate, right? So we prove, for example, we design a test. The soundness of the test in some sense gives us a certificate, and we search for a certificate, that satisfies the conditions, the checks that appear in our test. That's what we did in the previous lectures. And, like the certificate somehow, we just like design an algorithm that tries to search for the certificate itself, right? So here also there is a natural algorithm, which is it looks kind of different from the previous lectures because our certificate somehow involves a distribution here. But once I write it, hopefully you'll realize that it's not so unnatural. Find a distribution mu So, I'm going to find a distribution. My natural algorithm, still an inefficient one, but my natural algorithm is going to just try to find a distribution on W's in 0, 1 to the n. Okay. And to force that the fact that I'm only going to look for W which are 0, 1 to the n, I'm going to force that Wi square equals Wi for all I, which we've been doing for a while. I'm going to force that some Wi is alpha n. This is the size constraint that we checked. And now I have to force, a constraint that says that W should be a soluble set. Okay. So I'm going to force the following thing, and you'll tell me that this is a reasonable thing to do. So this is going to be a set of, this is going to be a set of tests in both W and L. These are the two variables. W is a soluble set. L is the, vector that satisfies all the equations in the set of equations indicated by W. So, and I'm going to normalize and look for, equations of length, at most, vectors, solution vectors of length at most 1. So the non-trivial thing here is this. So let's understand what it means, okay? In real life, Wi can take either 0 or 1 value, right? Wi being 1 means that that equation is included in the set indicated by W. When Wi is 1, the only way this equation is satisfied is if yi equals xi dot L, right? So this, the real world way to read this is to simply say that if Wi is 1, then yi is xi dot L. In other words, whenever W chooses an equation to be in the set it is constructing, then L should satisfy that equation. Okay. And so what we have discussed so far is that if I find a distribution mu which is supported on W's that satisfy all these constraints, and in addition is max coverage, right? Then we can actually produce a small list, right? That's what we've discussed so far, right? Again, stop me if things don't make sense, but I'm claiming that what we have done so far is prove that if I could find a distribution on 0, 1 to the n, I don't know what representation you are going to use to write this distribution down and what access you have, but imagine that there was some way to find a distribution mu in a way that you can sample from it efficiently. And you could find a distribution mu which is max coverage and satisfies all these constraints on W. Then in fact, you would be able to simply repeat this sampling argument that we did at the end and get a algorithm to return a small list, right? Stop me if it doesn't make sense, but I'm saying that this is what we just proved. We are going to, get an efficient version of this. And now you can almost see what the efficient version should be. Okay, so the first thing we're going to do is not try to find a distribution, but a pseudo distribution. Of what degree we'll see in a second, that minimizes and satisfies, let's call these constraints A sub WL. So at least I have written down something that syntactically makes sense, right? Let's call this, some number T for now, okay? Then at least um, we don't know what to do with this, but at least this algorithm is an n to the O of t time algorithm that seems to do something similar to what we had over here, right? It's a natural thing that if you took this class and you carried forward till lecture 12 of it, when only 8 people are left, then this is the natural thing you would do, right? You had a version with distributions. You simply replaced distribution with a pseudo distribution. You realize that this max coverage thing basically is this constraint. And so you did that. The question, okay, maybe I claimed it already, but let's maybe make sure that you understand that. Question, why is this efficiently soluble? By efficiently, I mean n to the O of t time. Why is that? I mean, I'm not simply finding a distribution that is consistent with AWL. I'm trying to find a distribution which minimizes this function. Why is that okay to do? Or why can I actually solve that problem?
Because the norm is convex.
Right, exactly. So this, this function here is a convex function of tilde EW. Now, tilde EW is a variable in your program. If you remember the very first or second lecture where we designed the SDP that solves the problem of finding a pseudo distribution, then remember that, this is a variable in there, and you are simply minimizing the L2 norm of this variable, which is a convex function of it. And in general, you can, solve the problem of finding a pseudo distribution subject to any convex constraint on, the values of the pseudo expectations. And so that's it. That's the reason why you can actually do this. Now, when I earlier referred to at the beginning of the lecture, this max entropy constraints, well, this is what I meant. They're very, they're much less, much less fancy than you might have imagined. In a certain sense, you needed, like as you saw earlier, we needed certain notion of coverage, right? Like, and the information theoretic sense in which this appears is the entropy of a distribution. We didn't really need this entropy. We needed, this sense of coverage, and we just happened to, minimize a certain norm. Now, entropy, by the way, if you remember, at least entropy of a distribution or negative entropy of a distribution is also, a convex function. And so, so negative entropy can be minimized, or equivalently entropy can be maximized. And so, it's the same principle. The fact that we could, if there was a way to do this optimization on a distribution, then, we could also maximize entropy subject to it. Here, the version of entropy that we need is simply this coverage property that we saw earlier. And that's what it appears as in here. So one way to interpret this as simply, this norm here as like some kind of a proxy for entropy. The reason I'm doing that, you can completely ignore it, by the way, right? Like this whole interpretation is not important. The reason I'm doing that is because there are several applications where you do have to, think about, different notions of entropy. So it's good to remember that, it's good to remember the instances and, the various specific surrogates, etc., that you use to, impose entropy constraints on a pseudo distribution. And so here is like, the L2 norm of pseudo expectation of W happens to be one such constraint that we're using here. Okay, good. So we saw this. The question is, well, there are two questions. How to analyze this? We did some analysis using anti-concentration earlier, but that use the fact that we had a distribution, etc. And we have to give an analysis that makes sense for pseudo distributions. And next, we have to give a rounding that makes sense for pseudo distributions. We can't quite sample from pseudo distributions even when they satisfy max entropy or whatever constraints. And so the sampling thing that we did at the end is not really an algorithm that we can apply on pseudo distributions. So I have to fix both these details, right? And so let's do that. We'll see how much time we have in terms of what we can do, but let's go ahead. And so the analysis, so if you remember, so our analysis earlier relied on anti-concentration of the good set G. In order for us to do the same analysis, to do the same type of analysis within the sum of squares, a framework, within this polynomial inequality system that we have, we will actually have to phrase the anti-concentration property as a certain polynomial inequality that is satisfied by the good set G. And so here's how we're going to do it, okay? And you're going to see like it's kind of a hack, but that's the best hack that we know so far. So this is a definition. Or actually, before definition, let's maybe do somewhat more of brainstorming. So let's look at G, right? So we know, so if you recall, delta anti-concentration of G means that for all directions V, we need that expectation. Oh, actually, let's maybe write the usual thing first and then convert it. So probability that XV is 0 is less than delta. This is what we wrote earlier, right? This is the meaning of anti-concentration, delta anti-concentration of the set G. Okay? I'm saying that, so I'm going to claim that this is same as expectation of indicator of this event being at most delta. Still agree? Like this is simply, the function that outputs 1 that x dot v is 0 and outputs 0 otherwise. Then I'm saying that the probability of xv equals 0 being at most delta is same as saying that, the expectation of this indicator of xv dot 0 is, at most delta. Still good? And I'm going towards this because, I want to phrase this fact. I want to phrase this fact as a certain polynomial inequality that G satisfies. Okay? So now, what are we going to do? So this indicator function, so, we want this to be, so, we are trying to phrase some condition for all vectors V. That's going to be hard. So we are going to try to phrase it as a polynomial inequality in variable V. For that, I need to take this indicator function and write it as a polynomial in V. Okay. Now, of course, there is no such polynomial. There is no such polynomial that computes the indicator function of x dot v equals 0. And so instead, we are going to settle with an approximation. So what is this function like? This function is like, if I plot what happens to this function as x dot v varies, then at 0, it's equal to 1. And then, it drops sharply. This is the function, right? This is a function that we actually have. What I'm going to do is, I'll try to construct a polynomial that looks like this. Actually, you know what? My polynomial is going to be a square, so it's always going to be positive. Maybe it's going to look like this. It's going to drop sharply, stay near 0. Now, it's a polynomial, so its a real nature has to show up at some point. So at some point, it definitely has to, it definitely has to rise up. It can't forever be low, right? Like, when you take the limit of a polynomial, when its variable goes to infinity, then it has to, go to either plus or minus infinity. So my polynomial is always positive. So on both sides, it will actually explode eventually, but will stay bounded in some interval. This is the kind of polynomial we'll choose. And I'm actually going to just claim the existence of this polynomial. You have to do some, approximation theory to construct it, which we will not do today. Okay, so I'm saying that, there is, so let's maybe make a claim. There is a univariate polynomial P such that P of 0 is 1. That's this property. And actually, I'm only going to, so because I have to control the expectation of this function, that's all I care about. I'll simply say this. So I want, let's maybe say this. So x drawn from G, P square. Let's maybe always work on P square so that we remember it's a square for all V in R to the D. What should I do? Okay, okay. Sorry, I'm just trying to find like the cleanest way where I have to do, where I can somehow, do without making multiple definitions. So let's make this a definition. And let's call this certifiable anti-concentration. Okay. We'll say that, G is, so let's say, okay, so we're going to say that G is good if there is a polynomial P on R such that P square of 0 is 1, and so let's also just make it final version. There's sum of squares proof of the fact okay, so this hopefully cuts down some other stuff that I was doing before, and hopefully this is enough. So what are we trying to do? We are trying to phrase the fact that G is anti-concentrated within sum of squares. Okay, so here is how we are doing it. We are saying that G is, so this number here is the degree required to claim that G is anti-concentrated. Okay, and so you will soon see that it's the same as the degree of this polynomial P. Okay, so we're going to say that G is T certifiably delta anti-concentrated if there is some polynomial P which is 1 at 0. Okay, and for so first of all, read this statement without sum of squares, because I kind of merged two things. And so without the sum of squares, the statement simply says that if I average over all the points in G, so this expectation is simply average. So let's be even more clear. So this is simply averaging over all xi's in G. And saying that if I compute the polynomial at xi inner product V, okay, and average it, then the average is at most delta. Okay. Now, without, so here's a fact that we'll try to simply verify. So this is a certain fact about, this is a certain fact about polynomials, right? Let's first convince ourselves that it does the same job. Okay. So notice that if G is delta anti-concentrated, then then sorry, the other way around. Suppose G is T certifiably delta anti-concentrated. Well, then G is also delta anti-concentrated. Let's try to quickly check this. Okay, this is this is like sanity check. This is like saying that the the criterion that we have for this certifiable anti-concentration is actually reasonable. So what is it saying? It's saying that so let's try to compute the probability that x dot v is 0. Okay, this is same as expectation, right? Still good. And so this is probability when okay, so this is probability when xi is chosen uniformly at random from G. Let me continue to use this notation. Sorry about that. And now here is the observation. This indicator function is 1 at 0. Okay, and it's 0 whenever x dot v is not 0, right? So I claim that this 1 x dot v is simply always upper bounded by this polynomial that I have. For all x's, so for all possible values of xi dot v, the indicator of x dot v equals 0 is upper bounded by p square of xi dot v. Why is this true? Well, this is always non-zero. This is always non-negative. So it's always at least 0, right? And so the only thing I need to check is whether at 0, which is the only point at which this indicator is 1, it's an upper bound or not. And it's a true upper bound because I know that p square of 0 is 1. Okay, so therefore I can write and now notice that the second condition means that this is at most delta. Okay, still good. So what this shows is that at least our polynomial reformulation of anti-concentration is reasonable. It does the same job. Okay, now it demands something more though. It doesn't just demand that there is such a polynomial. It in fact demands that there is a sum of squares proof of this inequality in the variable v. Okay, now because it's 637, let's not go into why we can actually get a polynomial that satisfies these two properties for G which are reasonable. But let me maybe just make a claim and not try to prove it right now. Fact, let G be a large enough IID sample from, let's say, the standard Gaussian distribution. Then G is O of 1 over delta square certifiably delta anti-concentrated. So what this is saying is that if when we first studied anti-concentration, we tried to prove the non-vacuousness of the definition. We now defined an alternate property. It by what we just observed, it is at least as strong as anti-concentration, but actually might be stronger. It's likely in fact stronger because we are demanding some SoS proof for a certain inequality. So we have to establish that it's a non-vacuous property. And I'm not going to prove it to you. I'm only going to claim that if I take a large enough sample from a standard Gaussian, then in fact G has a sum of squares proof, sum of squares certifiable anti-concentration, where the degree of the certificate is O of 1 over delta square. Okay, so now at least you can see where this earliest 1 over alpha, okay, wow. Where did I write the theorem statement at the very beginning? Here. So if you remember, there was this 1 over alpha square in the exponent. So remember that, the anti-concentration we're going to need is about alpha by 2, whatever, right? Think of eta as some fixed constant, forget about it. And so, this 1 over alpha square is simply the degree of SOS certifiable anti-concentration. And so even though, in real life, we didn't, like, for a real life proof, we didn't really need that much, time, etc. When we actually phrase anti-concentration within the SOS framework, we lose this running time simply because this is the only bound I know on SOS certifiable anti-concentration, even for like nice sets like random samples from a Gaussian. Anyway, so in the many open problems that relate to several questions we've studied in this class, finding out if this is the right, is there a better upper bound, is an outstanding open question, and like it has several applications, as in like it will not only improve like the algorithm we are studying today, it will actually likely improve several other algorithms. And so that's an outstanding question. And now okay, good. So we have formulated but let's quickly try to see at a high level how the rest of the algorithm is going to function. So what I haven't told you still is how the analysis proceeds with the certifiable anti-concentration. So what I have to now show you is that so I have to now give you a way to do the analysis instead of the anti-concentration property that we used earlier. And we have to do it in a way that allows for a simple rounding algorithm. And in particular, this rounding algorithm should not try to sample from a pseudo distribution. It should somehow only use low order pseudo moments, right? Okay, so because I am way too close to the end of our 3 hours, let me maybe just make a claim of how this is going to occur and try to tell you how it works and not try to prove this. So suppose G is T-certifiably delta anti-concentrated. Then, so remember our constraint system AWL. Well, we're going to prove that this derives in degree T the following fact. So what is this fact saying? Remember, like AWL has variables L, which is the linear function, like the vector we are hunting for. W is the soluble set corresponding to it. So the distribution, the pseudo distribution is jointly on W and L. And what we're saying is that if G is T certifiably anti-concentrated, then there is a degree T sum of squares proof that says that this funky quantity, so let's interpret this in a little bit, okay, is small. So what is this quantity? So if you just look at this guy, what is this saying? It's saying that L minus, oh, sorry, this is some only on the good set. This is saying that, L is close to L star in L2 distance. Like this bound is simply, L minus L star, the L2 distance. So what this is saying is that if I sum over the L2 distance of L minus L star, scaled by Wi, only on the good set. Again, remember, we don't know what the good set is. Okay, but if we do this, then this average is small. Okay, and believe it or not, this is the key fact. Like this is the analog of the statement that if, so here is a way to, okay, maybe I can explain it to you a little bit better. So imagine that W. So remember, W was W indicates the subset, right? So in the argument that we did in the first part of the lecture, we proved that if W intersects G sufficiently, in sufficiently large number of equations, then in fact, we get a good list, right? So in particular, imagine, so the intersection of W with G is simply this quantity. And if we normalize it, then this is the the normalized intersection of the set indicated by W with G, right? So imagine that this is large. Okay, for a second, imagine in fact it is 1. Imagine that W is exactly equal to 1. Okay, as in like imagine that W is simply the set G itself. Then notice that this simply is saying that the average in that particular case. So let's maybe imagine that this one. Then this inequality simply says that average over all possible and in that case it looks very good, right? It says that L is close to L star. That's what it says. Because this is nothing, right? This is simply 1. And so, okay, so anyway, like yeah, it's in the remaining time, it's kind of hard to justify why why this is the right encoding and why we can prove this. But let me at least sketch why this inequality is enough in like 3 minutes. Okay, so and in some sense, so the reason, so like one thing that's important is that we need to make sure that, so we have no guarantees on the B part. Like remember, we have no guarantees on B. So it's not a surprise that we can't prove any inequality about it, right? Like you can imagine that because we have absolutely no control over the B part, all that we are trying to prove is about the G part only, because that's what all our guarantees correspond to. We know that it's anti-concentrated. We know that L star satisfies it. We have no such guarantees about the B part. And so it's not maybe that big a surprise that the main statement we can prove is like something reasonable happens, for the points in G. And this is basically our statement. The reason this is enough, so let me maybe sketch that. So if this is true, so let mu be a pseudo distribution that satisfies AWL of degree bigger than or equal to T. Then just like in the previous lectures, we can take expectations of this inequality and we know that they have to hold true. So we know, for example, that we should have pseudo expectation Wi L minus L star should be small. This is simply taking expectations of this inequality or pseudo expectations of this inequality. And now see what's going to happen. So notice that so this mu is a pseudo distribution over both W and L. Okay, so we have like a cubic polynomial appearing in the variables of the pseudo distribution here. We're going to observe that Wi equals Wi square. Okay, because this is a constraint in AWL. And I'm going to reinterpret this as Wi L minus Wi L star. So that just allowed me to send in W by just squaring it. This is still good. And now what I'm going to use is the pseudo expectation Cauchy-Schwarz inequality to allow me to talk about, so maybe write it down and explain to you. To simply push this expectation inside. And so this is, in real world, this will be the Jensen, right? Like expectation of a norm is larger than norm of the expectation. So, I had a norm, I have an expectation, I took expectation inside. In pseudo expectation land, you can prove it using Cauchy-Schwarz. And now, I can rearrange this in the following way. So notice that L star is a constant. So this pseudo expectation in some sense only applies to Wi. So this is still small. And then I just pulled out the pseudo expectation Wi here. And so now, in my very hand wavy sketch, we are actually doing very good, because what are we saying? We have this non-negative weighting. We are saying that, this particular vector, now, for every I, this vector is different. Okay, because expectation of WIL could be different for different I's. But this is saying that, this vector on an average, like, I have a bunch of vectors, one for every I in, the good set. And on an average, those vectors are, close to L star. And at this point, and so, okay, so maybe I'll just describe the rounding because it's not going to make much sense. But basically, this statement allows us to do the following. Pick O of 1 over alpha samples at random. So just indices at random. And output that's it. And basically, and what we're going to do is, use this inequality here to prove that, one of them. So this is like it's like the analog of the average statement that we proved in the first part. That on an average, the intersection must be large, and therefore on an average the distance to L star must be close. We're going to use this inequality to prove, just by some averaging argument, that one of these vectors is going to be close to L star in L2 distance. So one of these vectors will satisfy, with like, let's say with 99% probability, one of the above vectors will be like, let's say some 100 alpha square. Actually, I didn't quite explain to you where it's going to come from. Let me just say it's going to be close. Let me just say it's going to be close to L star. Yeah, so sorry for the very rushed description of the algorithm.